So, good afternoon. Thanks, Biswa. My name is Govind. I am also from Indian Institute of Science, Computer Science Department. Arka talked about how to do address translation, right? How to take a virtual address and then convert it into a physical address. And once you give it to a physical address, of course, let's assume for the moment the cache does not contain this data, then it has to go somewhere and get the data. Where is it going to get it from? It's going to get it from the memory, which is typically the DRAM. Okay. So, in this lecture, we will try to understand how the DRAM functions, okay, what are the performance implications of that, and how it is going to affect the performance of your program. That is really what we want to see. Once again, feel free to stop and ask me questions. Okay. So, the question of course, is why should we study memory systems? It's going to be too difficult. I am going to stand here and then keep pressing that thing. Okay. Let us see. Many of you would have seen this diagram, right. This diagram shows how performance of processors, right, have improved over the years, and you could see that it is kind of going at the rate of 1.5x every 2x every 1.5 years. That is Moore's law, right. We all know about that. Okay. While processor performance is improving at this rate, memory performance does not necessarily keep increasing in the same way. Memory performance improvement is rather slow, more like 10%, okay, or lower per year, and it takes about 10 years to get 2x performance in memory. I'm talking about performance and not capacity, right. Performance meaning that how fast it can respond to things and how that is kind of improving over the years. So, as a result, what you see is that whenever people brag about Moore's law, they say processor performance keeps improving 2x in every 1.5 years. It is a very good thing, right. But then if you look at the whole picture, it is not a good thing, because the gap between the processor performance and memory performance is kind of widening more and more, and that is a bigger matter of concern. Of course, we try to address some of this gap using L1, L2, L3 caches. Okay, but beyond the caches, it has to be finally the memory, and the memory has to deliver the thing. So, that is one of the reasons why we want to study about memory and understand memory in a better way. This problem of widening distance between the processor and memory, right, has been called the memory wall way back in 1994, right. How many of you were born before that? Only a few. Okay. So, this problem was called the memory wall. Okay. And we address this initial problem using L1, L2 caches. Okay. Now, let us see. This is the picture that again try to summarize what we have seen so far. We have the processor, okay. We have the L1 cache, which is the first level cache from which data and the instructions could be fetched. We talk about the memory management unit, right. Arka talked about address translation, right, TLBs, they sit here, okay, in the memory management unit. Then of course, you have L2 cache, maybe L3 cache, and so on, right. And after all of these things, if the data is not in L1 cache, not in L2 cache, not in your L3 cache, and so on, eventually you have to come and pick up the data from memory, right. So, that is what we have to do. And today we are going to, in this lecture, we are going to talk more about how memory is organized, how memory performs, what are the important things in memory system, memory performance rather. Okay. A slightly modified picture of the same, okay, with multiple cores is actually shown here. You could see that now there are multiple cores, C1, C2, C3, okay, and each one may be having its private L1 cache. We will talk a little bit more about private and shared caches in the lecture in the afternoon when we talk about parallel architectures. For the time being, we will simply think of them as L1 cache, L2 cache, and so on. That understanding is good enough. Okay. And then if the data is not available in any of these caches, it has to go to the memory. So, there is something called the memory controller, which is actually attached to the processor, and that memory controller is the one which is going to give commands to memory and therefore get the data out of the memory. Okay. So, we are going to talk about the memory controller and the memory in this lecture today, right. So, and that is the picture, and a slightly better picture of that, I believe. Okay, yeah, okay. So, this also gives you some information about how much time it takes for each one of these levels in the memory hierarchy to respond. Typically, your L1 or L1 cache would respond in 1 to 2 cycles. Your L2 cache may be in tens of cycles. If you have an L3 cache, it might take about 20 cycles, 15 to 20 cycles or something like that, right. But if you miss in all of these caches, then of course, you have to go to main memory, and main memory today is in the order of few hundred cycles, depending on what your processor clock rate is and things like that. It is going to be in the order of few hundred cycles, right. Okay, now, Arka talked about virtual memory, demand paging and other things. So, where is secondary memory here? Huh? In the disk. Sorry, what did he say? Storage. Okay. So, that is not really shown here. What is the order of time there? Access time. Huh? Sorry? 1000 times of memory. Okay, that is a very optimistic estimate. Okay. Huh? Millions of cycles. Okay, maybe. So, we can just say milliseconds, right? It is in the order of milliseconds. Okay. We will again come back to this diagram in a slightly different way and then look at things also, but let us not, I just wanted to make sure that we should not confuse things, and we are essentially talking about main memory. Okay. So, the physical address which is translated by the address translation, okay, will actually try to fetch the data from the main memory if it is not already there in your caches. Okay. Here is one more picture of the same thing, right. Again, I will not go into all the details. You could again see there are multiple cores. This probably is more representative of today's processor. So, you can see that there are up to 16 cores here, each core having its own L1 data instruction and data cache, and maybe some level of L2 cache which is shared by some of the cores, and then another level of another L2 cache which is shared by some of the other cores and so on. And finally, we have an L3 cache which is basically shared by all the cores. Okay. So, you can see that as the hierarchy is going down, okay, you have more and more sharing, right. More cores are sharing the same resource. And of course, if the data is not there in any of these caches, it has to go and get it from the off chip main memory. Okay. This is a prettier picture of the same diagram. You could see that there are these cores, there is this L1 cache which is within it, which is not being shown, then there is an L2 cache, and of course, there is this DRAM interface and so on, right. And you could see DRAM in this form, and when you see DRAM in this form, you recognize it, right. How many of you have seen a desktop being opened up? Many of you. How many of you have bought a DRAM DIMM, either for your desktop or for your laptop? Okay. So, you could recognize this picture, right. That is the reason why I put this picture. Okay. Now, what are the issues when you go from single core to multi-core, and why memory performance is even more important in multi-core? So, one thing that we saw is the memory latency is an important thing, right, because processor clock cycles and memory latency in terms of processor clock cycles, there is a significant gap between them, correct. Whereas, when you go to multi-cores, it is not just the latency, it is also the bandwidth which is supplied by the memory. Bandwidth is essentially the amount of data that can be supplied in a unit time, right. That also is an important criteria, because now you have multiple cores, and each one of these cores wants certain amount of data to be supplied to the processor for its performance, right. So, all of these multiple cores together demanding more things, what is really happening actually stretches the bandwidth of memory. So, this problem is called bandwidth wall problem in 2009. Okay. So, essentially both latency and bandwidth are important, and the performance of memory in terms of both latency, the amount of time it takes to deliver the data, and bandwidth, the amount of data that it can deliver in unit time, they both are important parameters in terms of memory performance. And that is one reason why we want to study this in detail and make sure that we use this memory effectively, or if you are a computer architect, when you are designing things, you design things the right way, so that maximum performance can be extracted out of this. Okay. Okay. Now, when you talk about DIMMs and when you talk about these things being connected to the processor, the picture that should come to your mind is something like this. Okay. So, there is a CPU, there is a memory controller, and from the memory controller there could be a bus, okay, which could be divided into two channels, channel 1 and channel 2. Or there could be multiple memory controllers, and each one of these memory controllers can have their own channels. Right? Channels are nothing but a set of wires, okay, through which you can actually send commands to the memory and receive data from the memory. Okay. Send command and address to the memory and receive data from the memory, or send command, address and data to the memory and write data into the memory. Okay. We are going to see the organization of this memory in greater detail in this talk. Okay. So, again you could see that the DIMMs themselves could have rank 0, rank 1 and so on and so forth. Either a single DIMM can have 2 ranks, or multiple DIMMs can actually go into multiple ranks. So, each one of this chip that you see in your DIMM is basically what is called a device, okay, and that device itself contains multiple banks. Okay. We need to get into all of these details, okay, in order to understand the performance of memory. Okay. So, this picture is what you will remember, the DIMM that you have bought, and in the DIMM you will actually see multiple devices, and within each device you would see multiple banks. Has anybody seen multiple banks? I suppose not, right? You are not supposed to be able to see it's inside the chip. Okay. All right. And then if you go and look inside the bank, it is again organized as a 2-dimensional things, rows and columns, okay, tiles of rows and tiles of columns and so on and so on. Okay. So, whenever a processor gives a physical address and wants to access the data, right, it is first kind of understood to which memory controller it has to go to, or to which memory it has to go to, and therefore, to the appropriate memory controller, and from there to the appropriate rank, and then from there to the appropriate bank, and then from there to the appropriate row, and then from there to the appropriate column. So, it is multiple steps. Okay. So, the 32 bits of address, physical address that comes in is going to be divided. Some parts of it is going to be used to identify the rank, some parts of it is going to use to identify the bank, okay, and some part of it is going to identify the row, and some parts of it is going to be used for identifying the specific column, which tells you the exact byte or word or cache line that you want to access from the memory. Okay. So, you can now think of it in this hierarchical way. All right. Okay. Now, the same thing again we are going to go into a little bit more details. I want to take you up one step at a time. Okay. This will have some repetition, so bear with me on that. So, again you see the DIMM, okay, and then you see the devices. Okay. So, that is the DIMM, okay, and one part of it is what you are going to call as the rank. Okay. And then within a rank there are multiple devices, you could see multiple rectangles within the device, and each device has multiple banks, and each bank will have multiple rows, and each row will have multiple columns. Okay. So, the final thing within each column, whatever you see, that is probably the byte of data that you want to access. So, whenever a processor gives a address and wants to access, let us say, 1 byte from that, that possibly corresponds to this. You could also say that I do not want to access a byte, I want to access a word, or I want to access a cache line which is 64 bytes or 128 bytes depending on what your cache line size is, right. Then within that row a contiguous set of locations, right, is basically what is going to be accessed. And how does this access take place? Again, as I mentioned earlier, some part of the address is going to use to decide which rank it is. Here I have shown 2 ranks pictorially. Okay. So, which rank it is, and within that rank which bank it is, okay, and within that bank which row it is, okay, and within that row which column it is. So, some parts of the address are going to be used to decode the rank, some for the bank, some for the row, some for the column. Yeah. I am sorry. Okay. So, the question is how big is a row? That is your question, right. A row is typically of 2048 bytes or 4096 bytes or 8000 bytes, 8192 bytes. Okay. Typically, your cache lines are 64 bytes, 128 bytes or 32 bytes. So, multiple cache lines are contained in a single row, okay, and they are contiguous. Okay. Any other question? So, are you all with me? Is it lunch time? Are we feeling hungry, sleepy? No? Okay. All right. So, when you want to access the data, what really happens is that after you did a rank selection, after you did a bank selection, right, the bits which corresponds to row selection are actually sent, okay, to the row decoder. And when it goes to the row decoder, right, the corresponding row which is there in your DRAM device, okay, is being brought into what is called the row buffer. Okay. This is an important activity in accessing a DRAM. That means that the data that you want to access, the corresponding row, right, must be present in what is called a row buffer or a sense amp. Okay. It is called row buffer or sense amplifier. Okay. So, first the data has to be brought from the device to the row buffer. The row buffer is also a part of that thing, but it has to be brought there. Okay. And further accesses of column essentially take place from within that row buffer. So, if you want to access this particular column, then you access it from the row buffer. If you want to access some other column, you access it from that row buffer, sense amplifier. What if you want to access, let us say, some other column, some other row? Then this row has to be written back into the device and the next row has to be brought into the sense amp. The reason that it has to be written back is that when you are reading it, right, you would have discharged the charge from the capacitors, okay, and therefore, you have to go and write it back. And also, if there had been writes, okay, to any particular location, those writes, when they come as writes, will actually happen in the sense amp and they have to be copied back into the device. Okay. So, if you want to access a different row, a different column, I mean a different row and a different column, then this row first has to be written back and then the next row has to be brought into the row buffer, which is again called the row activation. The act of writing it back into the device is called precharge. Okay. So, we already know two things, one is precharge, another is activate. So, whenever you want to access a row, either that row should already be available in the row buffer or it should be brought into the row buffer, okay, or before you could bring it to the row buffer, anything which is there in the row buffer has to be precharged, has to be written back into the device. Then the row that you want has to be brought in, that is activate. Then you do a column access. So, there are three things that are involved in here, right, precharge, activate and column access, right. Yeah. Okay. So, each bank will have a row buffer, right. So, if you are going to access a different bank, a different row, a different bank and whatever row it is, okay, you can again bring that row into the row buffer of that bank. So, we are going to talk about bank level parallelism at a later point in time, where I will actually talk a little bit more about this and then give you an example how that really helps. Okay, yeah.
Where exactly is the decoding of the address taking place?
Inside the device.
Inside.
Okay, means if you are talking about these row decoders and column decoders, they are all inside the device.
Suppose I have some address,
Ah.
the address will point to a channel, then into a rank band, row, column.
Correct. So, some level of decoding happens. Okay. Well, you can actually say all of this goes on the channel, then appropriate decoding happens inside that. Okay. Others will actually ignore those signals.
First the channel is calculated, the whole address comes to the channel.
Yeah, and then inside it goes to both the ranks, only it is the relevant rank gets selected, the other one does not get selected.
Row and column is
Inside the device. Inside. Okay. Yeah. I'm sorry. To the cache. Okay. 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 So, we have only talked about column access. Okay. Right. After the data is being accessed, that data has to go to the memory controller. Okay. So, there is a transfer that is required. That transfer is going to take place on the memory bus, right, and that is also going to take some amount of time, because if you are going to transfer 64 bytes of data, right, that is 512 bits, correct. Your memory bus width may not be that wide, it may be smaller than that, which means that it may take multiple cycles to transfer the data, okay, which is accessed and then to be sent to the memory controller, and then from there it goes to the cache. Okay. So, now we have talked about the transfer, bus transfer also. So, we talked about precharge, we talked about activate, we talked about column access and then transfer. Okay. All of this are components of memory access. Okay. Again, I think the same concepts, but now in words. Activate is essentially bringing the data from the row into the row buffer. Read and write corresponds to basically the column access, right, and each one of these activities is going to take some number of cycles. You have to remember that. Precharge is the act of writing the data from the row buffer into the device. Okay. Okay, now let us look at the following thing. Suppose I want to access some data, right, and let us say that this data or this corresponding row is not there in the bank or in the row buffer of the bank. Then what happens? I have to do a precharge, activate and load. Let us say I want to access one more column from the same row. Now, because the row is already available in my row buffer, all I need to do is that I only need to do the load access, the read access alone. Okay. So, this is much faster compared to the first one. The first one took 3 times the amount of time, whereas the second one took only read. Of course, in both of these cases there is a transfer component which is involved, which I have not shown here. Okay. So, one more let us see, yeah, one more load, but this time to a different row. Then what happens is that again you have to go through precharge activate. So, this is called a row buffer miss. That means that whenever you are trying to access another row which is not there in the row buffer, that is called a row buffer miss. And when there is a row buffer miss, you have to do precharge, activate and read, and that takes more time. Whenever there is a row buffer hit, that means that the row is already there in the sense amp, you are going to have only, you are going to incur only the read time, which is faster. Copying to the row buffer? copying the data. Let us assume it as copying the data from reading the data from the device and then writing it into the sense amp. There is a latency, that is why your activate takes so many cycles. Okay? Each one of this takes some amount of time, maybe typically about 10 cycles, 12 cycles, whatever is the time. Okay? All right. Let us see. So, row buffer, so what I wanted to show there is that row buffer hits are faster, okay, and they consume less power. Row buffer misses are more expensive. Okay, the same thing with some animation now. Okay, let us go through this little quickly. Supposing let us say I want to access row 0, column 0, then that essentially makes sure that okay, the row decoders get that particular row and then you, my goodness, okay, you do an activate, it gets to the row buffer. Then of course, you want to access column 0, so you get column 0. I shouldn't have used this many animation, I guess. The next one, if you want to access column 1 of row 0, because it is already available in the row buffer, it is a row buffer hit and you are going to access it. And one more, I think if you want to access column 9 of row 0, again it is available in the row buffer, so again it is a hit. Whereas, if you want to access row 1, column 0, currently row 0 is there in the row buffer. So, this is a row buffer miss, and what you do is that you do a pre-charge, which basically writes the data back into the device, and then of course, you access the corresponding row and you get it to the row buffer, and after that your access happens. Okay? So, this is how the activities happen in a DRAM memory. Is that clear? Any questions so far? Yeah. Writing the, why are we doing pre-charge, right? When you read the data from the device into the sense amps, okay, you discharge some amount, okay, and therefore, you have to write it back to preserve the data. All right? That goes into some device level details, which we will not get into. Okay? So, there is a capacitor there. So, when you read it, the capacitor discharges and therefore, you are expected to write it back. Okay? And also, as I mentioned earlier, any writes that happen in between, those writes will only happen in the row buffer, right? And then that also needs to be reflected into the thing. That is why you always write it back. Any other questions? Okay. All right. So, again that in the form of some state transition diagrams. Okay. The device is typically idle. When you bring a particular row using activate, that row is active and you can do any amount of reads and writes on that row. Okay. But if you want to access a different row, then this row from the row buffer has to be written back. So, that is called pre-charge, and as far as this row is concerned, it is idle, there is nothing else in the row buffer now. So, the new row has to be brought in, okay. Again one more activate, and of course, you can again do the actions, right. That is essentially what it is. So, activate, pre-charge, and there are these reads and writes, which basically what we call as column access. Okay, there is one more thing called refresh. What is a refresh in a DRAM? Huh? Whoever is talking, can you just raise your hand and then talk a little louder? Yeah. The capacitor loses charge periodically, right? Even if you don't access something, right, the capacitor is going to lose some charge and it has to be recharged, and this happens in DRAMs, right, and therefore, they have to be charged again, and that is basically what is refresh. We will talk about refresh also and then see what are the implications of refresh. All right. Okay. So, here is some more details of the DRAM memory controller. Okay. The memory controller essentially is going to have a set of request buffers and response buffers. So, every time there is a memory request, they get queued in this, okay, and then the memory controller takes these requests, does certain things, find out when it will be ready to send a command, what command it has to send, and it generates the command, sends it to the memory. Okay, and whenever the data is accessed after x number of cycles, it is being brought through the bus to the memory controller, and it goes to the response buffers, and from there it goes to the caches. Okay. We are not going to see all the details, but this kind of gives you pictorially the idea of a set of request buffers and a response buffers, and some kind of arbitration which will actually choose this request in some way, okay, and then accordingly generate the commands. So, now you know that whenever I give a simple load from a processor, that load itself may have to be divided into multiple commands for the DRAM. Means let us say a processor is trying to do a load, the data is not available in any of the caches. Okay. So, you have to go and get it from memory. To memory you can simply think of it as a read, but then the memory controller is going to split this in terms of one or more commands depending on what state the memory is. If that particular row is already there in the row buffer, it can only give a read access. If that row is not there, it has to give a precharge, activate and read. So, the memory controller has to do appropriate action. So, every read command is going to be divided into one or more commands for the controller. In addition, the controller is also responsible for refreshing the memory. So, it has to periodically give those refresh requests, and it has to know which pages or which which pages in what banks needs to be refreshed. So, it will actually keep track of that, and it will generate appropriate refresh commands also to the memory, issue appropriate refresh commands also to the memory. So, that is the task of the memory controller. You can think of this as having the front end and the back end, okay, the controller and the back end. Okay. And here are some examples, a number of cycles for each one of these activities. As I mentioned, you could think that activate takes 10 cycles, precharge takes 10 cycles, and read or write takes maybe 8 cycles. Okay. And then there are certain timing constraints that you have to obey, because once you do an activate, okay, only after 10 cycles the data will be available in the row buffer. Then you can give a read access. Okay. Similarly, when you go from one bank to another bank, there is certain amount of time delay that you have to give. So, there are various timing constraints that are associated with the DRAM. We are not going to study all of them, but we will primarily talk about activate, precharge and read timings, okay, and maybe bus transfer timings. Those are the 4 things that we are going to focus on. Okay. In addition, there are a number of other parameters, number of other control parameters which also need to be obeyed, because when you go from a read to write, there is certain amount of time delay that you have to give. Okay. And how many number of writes you can do in a window of time frame is also defined. So, there are many other constraints which are there in the DRAM manual or the JEDEC standard, and the controller has to obey all of these things. Okay. It would take a lot more time to understand all of them. So, we will only do some of them here today, and that should give you a reasonable idea of how these DRAMs work. Okay. Yeah. No question is a stupid question. Right. Okay. Why don't we have more than one row buffer per bank? Okay. Keep thinking about this question. Okay. We are going to come back to that. Okay. Good question, not a stupid question at all. Right. Okay. Any other questions or any other concerns? So far, are we good? Okay. Yeah. Very good question. Okay. If you wait for another 3 slides, that is the topic that we are going to talk about. That is really where we are going to get. Okay. All right. Before we go into that, let us just talk about bank level parallelism. Okay. Somebody asked you, is there a row buffer per bank, what happens? Okay. So, this animation should possibly explain that. Okay. Here I have chosen banks from 2 different ranks, but they could be in the same rank also. Okay. It does not really matter. Okay. Let us assume that the first request is to bank A, okay, row 0, right. So, let us see what happens. You do precharge, activate and read. Let us say the next request is to bank B and row 1. Okay. Now, of course, I can do this, I am sorry, let us just go back one step. Okay. So, as soon as the channel becomes available, I can start doing the precharge, activate and other things if there is a row buffer miss. Let us assume initially it is a row buffer miss. But even when this bank is working on this sequence of requests, I can actually start this set of things on the other one. Remember, the memory controller is first going to give a precharge, and after x number of cycles it is going to give an activate signal. After another y number of cycles it is going to give the read signal. Okay. So, it is going to give these commands one at a time to the memory, but the memory controller knows that that bank A is being busy, okay, whereas bank B is actually idle at this point in time and my channel is available. So, I can go ahead and issue a precharge on this, or right, and therefore, bank B can work in parallel with bank A. So, this is basically the bank level parallelism that we are talking about. So, when this bank is working on getting row 0 into the row buffer, this bank is going to be working on getting row 1 into its row buffer. So, the two banks can now hold two row buffers concurrently, right, no problem, because each one has its own row buffer, all right. Now, let us say we want to do one more load from bank B, but this time row 2, right. Now, we know that this particular bank is going to be busy until this, okay, and the channel is also not available. Only after this is over, it can start working on the next one. Okay. Let us say in the meantime, we give another load. Okay. This diagram is possibly have to be shifted a little to the right. Okay. As soon as this read is over, it can possibly start doing this read. Okay. So, if you have multiple banks, there are multiple banks in a device, okay, and if you have multiple ranks, so you will have more number of banks, okay, you can now start doing these activities in parallel and try to get some level of parallelism. Okay. So, already there are multiple banks and for each bank there is one row buffer. Okay. Your question is why can't we have more row buffers per bank? Okay. That is an engineering question, right, you can think about it and we can see what benefits one would get from that. Okay. And the memory controller is going to remember that in this particular bank row 0 is in the row buffer, is active. In this particular bank row 1 is active, and after when this command has to be issued, it knows that only row 1 is active, and if I want to get row 2, I have to do the precharge and then I have to do the activate and then I have to do the read. It knows when exactly the channels are available and when the channels are not available. It is the one which is going to schedule all the transfers. So, once it puts the read, it has to essentially reserve the channel so that the data can come, right, because once you read the data from the row buffer, it cannot wait anywhere, it has to come back. So, it has to be transferred. So, the memory controller essentially reserves or does all of this scheduling. Okay. Okay. Sure. Yeah. Okay. Yeah. Okay. So, to be correct, so I have shown this to be a bank in a single rank, okay. This to be another bank in a single rank, okay. I called this as A and okay, I should have actually called this as C, okay. I understand your point. So, this should have been on this, right. Okay. Okay. Let me just try to clarify here, okay. That is the same diagram which is over here. What I showed as a device or a chip is over here, this rectangle. So, there are multiple such rectangles. In fact, there will be about 8 rectangles. So, there are 8 devices, which is what you see in your DIM, okay, and all of these things together form a word or a, let us say, form a word, okay. All of these devices put together form a word, okay. So, there is some kind of a device level parallelism which I do not talk about, Okay. So, when this particular device bank 0 is being accessed, row 0 is being accessed, that same thing happens across all of these devices in the same DIMM. Okay. That is how you get a full word. I did not go into the details. Full word in the sense of, see, you can think of each one of these devices as having 8 bits. Okay. So, across this the word is going to be spread. No, 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 no. The okay. How do I answer? Okay. Let me try to give a slightly let me give a quick answer, but may not necessarily be the correct answer. So, some part of the word is what you have seen there in the diagram. Okay. The similar part of the word is in the same row, same bank of another device. The third part of the row is in the same row, same bank of the third device, and so on. Right? I can kind of slice it. Okay. Slice it. Think of each device as being 1 bit. Okay. Then 8 bits would be across 8 devices. So, if I want to get a full 8 bit, I have to access all of these devices, right, and the same bank, same row, same column, right. That together would give me 8 bits, let us say. That probably would answer your question. Yeah. Well, 8 bits, 8 bytes, whichever way, it depends on the size of the device, right. Okay. How many bits it can hold? Each column typically is said to be of 1 byte. Okay. And typically you access in terms of cache lines, which is 32 bytes or 64 bytes. Okay. All right. Let us see. Okay. Let us talk about refresh a little bit. As we mentioned earlier, refresh is required to ensure that the data stays in the DRAM. Okay. And typically a refresh needs to be done maybe once every 34 milliseconds in the current technology. But if the device is hot, that means that at higher temperatures, okay, the retention time actually reduces, and it is safer to do this refresh, let us say once every 32 milliseconds. Does not really matter. The device, this is device specific, and the manufacturer is going to tell how often the refresh has to be done. Okay. Now, in this 32 milliseconds, all the rows in a bank and all the banks need to be refreshed. Okay. But across banks you can exploit bank level parallelism, they can be refreshed in parallel, but within a bank, right, page after page or row after row, everything has to be refreshed. Okay. A single refresh might take something like 20 cycles, right. Therefore, if you have something like 128K pages or 128K rows, I am going to use the word row and pages somewhat equivalently, right. When I say row buffer hit, okay, it means that the particular row or page is there in the sense amp, because they use the term page also in the DRAMs. But if you are very comfortable, we can stick to row. So, there are 120, supposing let us say there are 128K rows, right, in a bank, then all of these 128K rows need to be refreshed, each one of them take 20 cycles. Therefore, you will take roughly about 2.6 milliseconds or something, right. So, that is the refresh, and this 2.6 milliseconds has to be taken only to refresh the device, and you have to do it once every 32 milliseconds. That means that in a 32 millisecond window, you have the DRAM device available to you only for less than 30 milliseconds, because in the other 2 milliseconds or 2.6 milliseconds, you are going to be busy doing the refresh. Okay. You can, for now you can think of all of these refresh happening together, but the memory controller is smart enough and it can schedule these refreshes in some way. Okay. They need not have to be contiguous, but it still has to do all of the refreshes within that 32 millisecond window. Okay. So, this picture that I am going to show you will kind of show it to you as contiguous, but do not think that it always has to happen as contiguous. So, you could have periodic accesses to your device, but then there is going to be a refresh. And then after the refresh again you could have accesses, and again after another 32 milliseconds you have to do the refresh. So, here I am showing that the refresh is happening together, but this need not necessarily have to be this way. But the essential effect is that, as I mentioned earlier, if I am assuming certain amount of DRAM size, where each row is 2 kilobyte row, right. It is organized as 16 banks, then I will have a total of, let us say, about 128K banks. Each row takes about 20 nanoseconds to refresh, then this whole thing is going to take this much time too. That essentially means that, okay, if I am taking 64 milliseconds, then it is a 4% overhead. If I am taking 32 milliseconds, it might be a 8% overhead. That means that the device is not available for regular read write accesses during this period of time. Okay? That is what it really means. Okay? Correct? So, some maintenance is happening and the device is not available for your normal reads and writes. Okay? So, that itself is going to take some performance out of the device. That is one way to look at it. Correct? Okay. Now, somebody talked about how are the accesses going to be ordered. Yeah, sure.
Why can't we recharge this capacitor, pages parallelly? Why are we doing it sequentially? It is taking a lot of time.
Again, I will not go into the details, that has something to do with the device, okay, how this could be done. You can do things in parallel across banks, but not within a bank. Okay. If we have the power, we could do everything in parallel, right, and we could get it done. Unfortunately, not all of it can be done. Okay. So, we are going to talk about the access ordering. Okay. The memory controller is the one which is going to receive the request for accessing data. Okay. So, let us focus on a specific bank, and let us say these are the sequence of requests that it receives in that order. Okay. This is the first request, this is the second, third, fourth, and so on, right. And as it services these requests, newer requests might come in. Okay. So, the first request is to row 0, column 0 of a particular bank, and let us assume that initially the row buffer is empty or it contains something else. So, the memory controller is going to detect that this is a row buffer miss. So, it will give the activate signal and it will try to get the row into the row buffer. And after the data has come to the row buffer, it will try to do what happened. Okay. It will try to do a read and read the data, right. The next request is also to row 0, but column 1. In this case, it is a row buffer hit, therefore, it will only do a column access or read and it will access the data. Right. Now, what is the third request? The third request is to row 1. So, what do we have to do now? We have to do a precharge. So, let us see how that happens. So, as soon as the memory controller understands the next request is to row 1, now we are processing requests in order. Okay. So, the next request is to row 1 in this particular bank. So, it has to precharge this, not sure when it will work, okay, now, right, and then it has to activate the next row, right, and of course, the next row, I am sorry, it either goes too fast or too slow, and of course, the next one is access. Then again what happens? What is the next access? The next access is to row 0. That means that again I have to do a precharge, activate and then access. So, you already know what is that we are doing wrong. What are we doing wrong? We are processing the request in order, right. That is what is causing the problem, right. If the memory controller is smart and if it sees, okay, let us go back 2 steps, right. If it sees that even though that there is an earlier request for row 1, there are subsequent requests for row 0, which is already active in my row buffer, and if I can process these things, then I can avoid at least one row buffer miss, right. Because if I have processed this, row 1 would have come, and therefore, when I want to do this, I would have a row buffer miss. That row buffer miss I can avoid if I try to process these things out of order, right. Therefore, the memory controller which is doing the access order scheduling, in the case of a simple FCFS, would actually schedule this request because this has come earlier, and therefore, would incur an additional row buffer miss for this particular thing. Whereas, a smarter memory controller would reorder these requests and send those two requests earlier, and therefore, avoid that particular row buffer miss. So, what is that we gain because of that? Those accesses will not incur an activate and a precharge, and therefore, they could be done only with 10 cycles rather than 30 cycles. Okay. So, that is really what I wanted to get into. So, let us see, that is basically what an FRFCS is, okay. Gives preference to row buffer hit, and within that it will do FCFS. Okay. I have already explained this. So, this is a commonly used scheduling policy, and you can see that row hits first and then oldest first. Okay. If there are no requests to the current row, right, then it will take the oldest request, first come first serve, right. As long as there is a row hit, it will continue to satisfy that. So, what is the downside of this FRFCFS? Huh? Sorry? It has to be buffered somewhere. It is going to be there in the request buffer. We know that.
After serving the request buffer, to preserve in order.
So, it has to park it somewhere. Let's say it has to park it somewhere. That is fine. Any other problem that we see? I am sorry, the first part of it I missed it. Sorry. Overhead of grouping them and things like that. Any, starvation, fairness issues might come into picture. Okay. So, again there are research work that takes care of some of these things, and one could do other things on that. Okay. So, here is the same example. Okay. You can now try to see this faster. I am not going to say. So, row 0 column 0, then after that row 1 column, sorry, row 0 column 1, then it takes row 0 column 4, because this causes a row buffer hit. Okay. And in the meantime, you could see one more request has come for row 0, even that would be satisfied before you go to row 1 column 0. Okay. So, that is how FRFCS or memory access scheduling happens, and it essentially saves, in this particular example, one additional precharge and activator, okay, for this sequence, and that is the gain that you get. Okay. So, hopefully, you will do some hands on this. Okay. Okay. Now, in the next 30 minutes or so, we are going to talk a little bit more about emerging technologies, some aspects of stacked DRAMs, and how to use them as a last, I mean, we already talked about L1, L2, L3. So, maybe one more level of cache. Okay. That is really what you are going to do. Yeah.
Just like that, the buffers are maintained for each bank, right?
The row buffer, there is a row buffer per bank.
Not the row buffer, the request buffer.
Oh, the request buffer. The requests are maintained in the memory controller.
Is there a pending read or write request buffer, or is it buffers for every single bank?
Okay. So, go back to this diagram. Okay. What is your question?
Yes. On the memory controller, is this buffer like read or write, pending read or write request
Okay.
maintained for each of the banks, or is it maintained in a single? Is a single buffer?
That is an internal information, right. So, it could possibly maintain it on a per bank basis so that it can easily access it. It could do that, yeah. Yeah, it's an internal organization, right? So that's why you see multiple queues. Honestly, I do not know to what extent whether it keeps it at the bank level or whether it keeps it at the rank level. That's an internal detail. Yeah.
From last 2 days, what I learned is that we're doing optimization at every level. Okay? So we're doing optimization at this level too. Can these two conflicts start conflicting? Because
Okay.
issuing requests thinking something.
Sorry, what is the issue?
Not the compiler. The processor is issuing load and store requests thinking something like it's trying to parallelize its operations, and when these come here, now it tries to do parallelization at its level.
Possible, right? So our question is that the processor is doing certain things, and from its level it is trying to optimize and order things in certain particular ways. And now here the memory controller is going to look at its view and then say that, look, if I want to do this, I am going to optimize these things. Would these things cause conflict? At some place it is definitely going to, but overall the idea is at every level we want to speed up those requests. Okay? So something might get delayed or stalled, right?
What are memory bursts?
Memory bursts. Okay.
Bursts, I mean, the read bursts and write bursts.
Okay. So I mentioned to you about these transfers, correct? So once the data is fetched, it has to be transferred back to the memory controller. It's going to take in multiple cycles. So this is basically the burst that they were referring to. Okay.
This incurs additional energy.
It incurs energy. Is that your question? Yeah. Yes. Yes. Yeah. Okay. It's related to the number of cycles. Okay. Let's go back to the slide. Emerging memory technologies. Okay. Okay. So again, Arka talked about non-volatile memory, right? And there are these different types of non-volatile memory. We will not go into the device aspects of these memory, but essentially these are again accessible in a way which is similar to your SRAM or DRAM, more like your DRAM, let us say, okay, byte addressable and accessible. Okay. And these are different technologies. The nice thing about them is that they are non-volatile and they do not require any refresh. Okay. We will particularly talk about this phase change memory in the next slide. Okay. And they have their own characteristics. The read access time may be somewhat similar to the read access time of DRAM, but their capacity is significantly higher, and maybe the write access time is also higher. Okay. So this diagram kind of puts everything in perspective. So if you look at your L1, L2 caches, they are somewhere over here. Their access time is in the order of 2 power 1 or 2 power 2 or 2 power 3 cycles. Okay. And they are SRAMs, right. Then if you come from there, then you could possibly have what is called this embedded DRAM, okay, which is some kind of on chip DRAM, which could have access time which is in the order of few tens of cycles. Then of course, we have the DRAM which we talked about, memory, which would have access time in the order of few hundreds of cycles. Okay, here I have put 2 power 9, but it is anywhere from 2 power 8 to 2 power 10, depending on how fast your clock cycle is. So that is why this purple ellipse here shows that could potentially be what your access time is. Okay. And then of course, we have this PCM, which is the phase change memory, okay, whose read access time is somewhat similar to the DRAM access time, but its write access time is little bit more, right. It is non-volatile, but its durability is limited, right. You can only do certain number of reads and writes on that memory, after which the device fails. Okay. So that's one other aspect to this phase change memory or some of these non-volatile memory. Okay. Then you go further, you have these flash drives, right, that is there in the next level, and these are accesses, block level accesses, right. You talk about accessing one full block, not byte addressable, block addressable devices. Okay. And of course, you have the hard disks over there. So, you can see the hard disk is in the order of 2 power 22 cycles. So, somebody said millions. So, good. So, 4 million cycles what you are talking about. Okay. So, this is really where they fit in this spectrum. Okay. So, very quick overview of the phase change memory, right. So, in the phase change memory, the data is stored in a special material, okay, and this material's resistance actually changes. The resistance changes because it goes through two phases. Somehow this is not working that well. Okay. So, it goes through two phases, one called the amorphous phase, which is a high resistivity phase, and the other one is a crystalline phase, which is the low resistivity phase. By passing some current, you can actually make this material go from one phase to the other. That is like storing a 0 or a 1, and then you measure the resistivity, then you know what is being stored there. Okay. So, this is how this device stores information, right. This is how this device stores information, and once it is in a particular state, it will continue to remain in that state. There is no leakage, right. So, there is no need for any refresh here, right. But the number of reads and writes that you can do, or the number of reads that you can writes that you can do is kind of limited. When I say limited, it is not few, it may be few million, okay, but that's still limited. Okay. So, it has the property of non-volatility, that means that even when the power goes, it will remain in whatever state it was earlier, and therefore, the data is kind of retained, and it has it does not have any leakage energy or leakage power, and that it also does not require refresh, and as I mentioned earlier, it has a high write latency and a high write energy, because the write is essentially to change the state of this device or the material, and that involves higher energy, and of course, it has endurance issues. That means that you can only do something like 10 power 8 or 10 power 9 writes, after which the device dies. Okay. Now that you have PCM, there are so the important advantage of PCM is that it gives you two advantages. One is it is non-volatile, okay. It does not require refresh, and it can offer you higher capacity. So, three advantages you can think in terms of. So, how can we use DRAM and PCM together, or can we use PCM all the way? What are the advantages and disadvantages, or how can we have different kinds of memory organization? So, in the leftmost diagram, you see that it is only a DRAM, sorry, in the go back one step. So, you can see a DRAM only organization, which is what we have seen initially. In the middle diagram, you have a hybrid organization where you have both PCM and DRAM. Here you can actually treat DRAM as one level of cache in front of PCM. That is one way of looking at it. So, the DRAM has a higher capacity, right, and the PCM has a higher capacity, and the DRAM is a cache in front of the PCM, and if the data is not there in any of the lower level caches, then of course, it can come to DRAM and it can access, but if the data is not also there in the DRAM, it can possibly transfer it from the PCM to the DRAM. Okay? That is a possibility, that is another way by which you can organize. Of course, you can organize it all as PCM, okay? But then here you have the issues relating to higher write energy and endurance related issues. Okay. So, again there are some research work which talk about how to do this organization, what are the advantages and so on and so forth. All right. Now, let us go back and then talk a little bit more about stacked DRAMs and DRAM caches. Remember, in one of the earlier diagrams I talked about embedded DRAM, which is some kind of a DRAM on a processor. but that is a different kind of a DRAM. I am not going to talk about that, but something very similar to that is what is called a DRAM cache, where I would possibly build a DRAM on the same chip itself. How do? We can do it using what is called die stacking technology. Okay? That can be done. I will show you that in the next diagram. And then I could potentially have a DRAM which I could use as the last level of cache. So, already we talked about L1, L2, maybe L3, okay, which are called the last level SRAM caches. But below that level, before you go to the off chip memory, on the processor itself, you see this nice rectangle here, which is basically what a processor is, a socket, right. It has multiple cores, multiple levels of caches and the memory controller all into that. Now, I am going to add possibly a DRAM also into this, okay. And when I add this DRAM, it gives me an interesting possibility to now talk about a cache. Okay, before I say this, okay, what would be the size of an L1 cache in your discussion when you discuss what is the size of the L1 cache? 8 KB, 32 KB, 64 KB. What about an L2 cache? 256 KB. So, many of you have an Intel processor in your laptop. So, 256 KB is a reasonable thing to talk about. Anybody? Okay, what would be that of an L3 cache? 2 MB? Good. So, how would you like if I give you a 1 GB cache? Right? That would be wonderful, isn't it? Like we talked about kilobytes of L1 cache, kilobytes of L2 cache, hundreds of kilobytes of L2 cache, few megabytes, right, 2 megabytes, 4 megabytes of L3 cache. Now, suddenly I say, okay, all right, I will give you 512 megabytes of L4 cache or 1 gigabyte of L4 cache, right. Then a lot of things that now you can have in your L4 cache, right. But remember, I am trying to cheat you, right. How many of you agree with me that I am trying to cheat you? Many of you should, okay. What is the access time of L1 cache? Few cycles. Access time of L2 cache? Maybe 5-10 cycles. Access time of L3 cache? 20 cycles. When I am going to put you a 1 gigabyte of L4 cache, am I going to give you in 10 cycles, 20 cycles? No. I am going to give you maybe in 100 cycles, right. So, as the hierarchy goes, the size increases, the access time also has to increase, right. When I say that I am going to give you an L4 cache of 1 gigabyte and you were all excited, right, I did not tell you that it is also going to have a larger access time. Definitely less than the access time of memory, maybe, okay, but still very large, right. So, that is really what this DRAM cache is all about, okay. Going to give you a huge, right, cache which is on chip, right, and going to give you an access time which is going to be somewhat similar to the access time of memory in fact, okay, not very different. Then you would ask me, why do I want that? I might as well go to off chip memory and get it. So, why do you even take the trouble of putting a stacked DRAM here, right? Any answers? There will be a bus delay. Okay, bus is fine. I am not sure about the delay part, but let us say bus. Okay, something else. Very good. So, there is a huge bandwidth that I am going to get if I am going to put it on chip as opposed to off chip. My off chip bandwidths are always limited because it is limited based on the pin counts on my device. Off chip means outside the device, right. So, outside my processor, how many ever pins I can get, my bandwidth is going to be limited by that, right. Whereas, if it is on chip, okay, I can actually increase the channel width, I can increase the bus width, and I can get huge bandwidth gains on that. Okay? And particularly it is going to go through what are called the TSVs, which can operate at a greater clock rate and so on and so forth. So, there is a bandwidth gain that we are also talking about here when we are talking about the DRAM cache, not the latency gains, but more in terms of bandwidth gains. Okay. So, larger capacity, bandwidth gain, perhaps similar latency as the DRAM. That is really what it is. Okay. Now, let us look at what are the challenges involved in doing this, but before that I said I will talk very briefly about the stacked DRAM. The stacked DRAM itself is done by stacking layers one on top of the other, and I may not go into too much of detail. So, you can see that the processor cores, and then on top of that you could see DRAM cores stacked one on top of the other, and they are connected by means of what are called these TSVs or through silicon vias, okay, which are kind of the conducting things. Okay. Could be done that way. It could also be done in what is called a 2.5D stacked DRAM, where you have processor cores being stacked or being put in one side, and the memory is being stacked on the other side, and they are connected by means of this silicon interposer. Okay. So, in either case what is really happening is that the processor and the stacked memory are together in a single chip, and that is why it has this higher bandwidth advantage. Okay, whether it is this one or this one, does not really matter. Okay. So, yeah, sorry, one thing I forgot to mention here is that, of course, I am going to talk about using this stacked DRAM as a last level of cache, but one could also use this as a part of memory. How many of you know about the Xeon Phi processor? KNL, Knight's Landing. So, what do you know about the Xeon Phi processor in the connection of stacked DRAM? Do you remember that word? Somebody else also raised their hand on that side. Okay. Go back and check what is MCDRAM, right? MCDRAM, okay? That is a stacked DRAM, okay? And you could use that either as a cache or as a part of memory. Okay, when I say as a part of the memory, then what is going to happen? In the earlier diagram, you should know that my off chip memory will contain some part of the address space, and my on chip memory, which is the stacked DRAM, could contain some other parts of my address space, and the page translation mechanism that the operating system is controlling can actually decide which page has to be on chip and which page has to be off chip. It can allocate it accordingly. That is one simple way of looking at it, right? And that is a way by which I can use my stacked DRAM as a part of memory. If my operating system understands that I have a stacked DRAM and understands the advantages of a stacked DRAM, then it can allocate some parts of the memory on the stacked DRAM and some parts of the memory on the off chip DRAM, okay? And my program can take advantage of that. In fact, one could do this in KNL. Okay. Okay. Again, so let us go back to this particular diagram. Okay. Here you see that, as we mentioned earlier, we have your L1 cache, your L2 cache, okay. And then after that you are going to have your DRAM cache, which is basically a stacked DRAM cache, okay. And this is going to be your last level of cache. Let me just try to in the next 10 minutes or so try to illustrate some problems in the stacked DRAM cache and talk about various solutions that have been proposed to address this. Oops, sorry, why did it go so fast? Okay. Now, this is a wrong diagram. Okay. Okay. I think just ignore this green part of the diagram for the time being. Okay. So, after the processor has given an address which has been converted into a physical address, and let us say this address or this data is not there in your caches, any of your L1, L2 caches, correct. So, that physical address, okay, is what you have, and if I have a DRAM cache, how do I use this physical address and access the data? That is the question, right. This is the same question which you would have asked for your L2 cache or for your L3 SRAM cache. Okay. You want to now ask the same question for your last level DRAM cache. The difference here is that there is a little bit more complication that is involved in here. Okay. In the case of your DRAM cache, you first take that physical address, okay, and you do some kind of a hashing, which is basically taking off some bits and then looking at some other bits, I mean the middle x number of bits or whatever it is, which tells you what is the set index, that is essentially what you get, okay, the set index. But then that alone is not enough for you, because along with that set index, if it is a set associative cache, you also need to know in which way it is available. That also is something that you need to add. I put this as offset, but you basically call this as the way number, right, because the data is going to be available there, right. And essentially what happens is that you are going to go use this address, index that particular row, right, and first of all you have to know, okay, you have to know where the data is. So, you basically have to index into that row and then access the data. Okay. There are a few things that I have actually not said, I am going to talk about that now, right. So, whenever you go, you talk about a cache organization, particularly a set associative cache organization, what you do is that you have the address, you index into that set, you get all the tags, do a tag comparison, and then that tag comparison will tell you whether the data is available in that cache or not in the cache. And if it is available, in what way it is available? It is available in way 0, way 1, way 2, way 30, whatever it is, it is going to tell you that, correct. And let us say if it is available in way 30, then you have to go and access the data from way 30 and then get the data out, right. This is what you normally do in any cache. Now, if you are going to do this in a DRAM cache, okay, the first thing is to do tag check. First of all, fetch the tag and then do the tag check, right. For simplicity, let us assume that the metadata is stored in some kind of an SRAM. Okay. This is what I have not talked about. If it is stored in some kind of an SRAM, then of course, I can use this physical address, take a hash of that, identify what is the corresponding set, and I can get the tag for all of those sets, okay, the tags for all of those sets, and then do a tag match, and then depending on what the tag match is, I can get the way offset or the way number, the so called way number. Now, if I add that way number appropriately with this set number, which is basically this is a set number and this is a way number, if I add these two things, it tells me where exactly the data would be available. Now, I have to go access the data from the DRAM. So, what has happened is now you now have an address in the DRAM and you want to access that particular address in your DRAM cache. So, what does it involve? It is again going to involve activate, precharge, possibly precharge, activate and column access. Okay. If your cache has been an SRAM cache, you would not necessarily be talking about all of these things. If your cache had been an SRAM cache, you could have potentially accessed all of the data in parallel, all of the tags in parallel, could have done tag comparisons and could have taken the data out of the multiplexer. But your cache is a DRAM cache. If I want to get the data from all these 32 ways, right, that might involve me getting the entire row, possibly from the row buffer, right, and then taking this out. This is much larger thing, okay. So, you may not want to necessarily do that, right. So essentially what you need to do is that you first do the tag check, and after the tag check is done, if the data is available in your DRAM cache, you go to that specific memory location and then get that from that particular way number. So, essentially you need to calculate the address in the DRAM cache even before you access the data, right, because you need to identify what is the way number and you have to get that thing from that particular way, right. Okay. There are some designs that have been done to overcome this kind of access, which is first accessing the tags and then the thing. So, one other thing that you should also know is that, okay, if I have, okay, so let me go to the next slide. Okay. As I said earlier, my DRAM cache is going to be bigger, okay, and because it is bigger, if I talk about cache line sizes at the granularity of 64 bytes, okay, how big is going to be my metadata? That is the first question you want to ask. Okay. And if you are talking about even cache DRAM cache of size few hundred megabytes, they would require metadata in the order of few tens of megabytes. Okay. For example, if I am talking about a 1 GB of DRAM cache, then I might require maybe about 2 MB or 4 MB of metadata. 2 MB of metadata in SRAM is very expensive, right, and that is why your L3 SRAM cache is no bigger than 2 MB or 4 MB. Now, if you say that I want to have this for a metadata, which is for my next level cache, okay, the question, probable question to answer would be like, would you be better off by doubling your SRAM cache size rather than having this stacked DRAM cache? Okay. So, there are issues and challenges in actually having this much of SRAM structure, okay, and therefore, what people want to do is that, so this is a specific example for a particular things. Okay. So, either you should increase your block size instead of 64 bytes, you might want to talk in terms of either 512, 1024 or 2 kilobyte block sizes, and when you do that, obviously your metadata structure overhead would come down by the same factor. Okay. But the disadvantage there is that if you have large block, then you would try to bring that large block, okay, and that would have a large block from the off chip DRAM to the on chip DRAM cache, and that would essentially waste your off chip DRAM off chip bandwidth. Okay. It would also mean that if there is not enough spatial locality, the data that you bring in may not be very useful, because when I am bringing in, let us say 2 kilobytes of data from my off chip memory to my DRAM cache, right, that is significant amount of data, right, and I may not necessarily use all of it, which means there is a wasted bandwidth as well as wasted cache space. Okay. So, there are two possible design approaches. One is to build this SRAM tags, that is the tags in SRAM or metadata in SRAM, for which typically you go for large block sizes, or if you want to have tags in DRAM, you could even possibly go with small block sizes. Okay. I will talk about one particular organization and then we will quickly stop, we can skip these things. Okay. So, again we will talk about this particular organization where in one of these organizations what they do is that they talk about a cache which instead of having 32 ways, okay, is going to have 29 ways and going to use some part of the data as tag. So, essentially what I want to do is that, again, tags are going to be, when I talk about tags in DRAM cache, okay, what is going to happen is that I have to store the tags in some place. I first have to access them and then I have to do a tag check and then I have to understand which way I have to go and access, and then I have to give that address and then access the data, right. If I store tags and data in two different places in my DRAM, then definitely I am going to incur, right, possibly 2 row buffer misses, right. To optimize that, what these people do is that they try to store the tags for all the ways, okay, in the same row buffer itself. So, you can see that metadata and the data are put together in the same page. Okay. So, this is one particular cache organization, and what happens here is that you can actually take that physical address, oh my goodness, Okay, you can actually take that physical address, okay, hash that, and then you can index it, get the tags first. The tags might be 3 times 64 bytes. You access all of them, okay, and then you do a tag check, and after you do the tag check, you identify which way it is. Maybe it is the 10th way. So, therefore, you go and access that particular location and get your data out. So, this is one organization. Another organization in which you talk about your DRAM cache as an alloy cache of direct mapped cache. Okay. What they do is that they basically assume that this cache, okay, is a direct mapped cache. So, associativity is 1. Therefore, once I know the hash address of the physical memory, I know if the data is available, it could only be available here. So, what I do is that I take that address, go access that, get the data and the tag together from that particular location, and then see whether it matches. If it matches, I have a hit. If it does not match, it is a miss, then I have to go to off chip DRAM. So, one thing you would have noticed in that is this: if it is a hit in the case of a DRAM cache, then you go through all of these things and get the data after a DRAM access. And if it is a miss, after all these things you have to go to off chip DRAM, which is going to cause again another few hundred cycles of delay. So, it is important to avoid this. So, it is important to do certain predictions, and that is why you see here some kind of a mismap prediction, okay, which basically tries to see whether is this data going to be available in my DRAM cache or not. If it is not going to be available, then I will not go through all of these hurdles and then find out that the data is not available, do the tag match and then identify that my data is not available. I would directly go, after checking this mismap, I will directly go and access the off chip DRAM. So, this mismap is again an SRAM structure which could be checked rather quickly. So, these are some possible organizations of DRAM cache. I think I will stop here, and then possibly in the afternoon you will have a lab session which would do mostly with DRAMs, okay, as memory. We will not talk so much about DRAM caches, because DRAM cache is some recent research activity. I thought that I would also talk to you about, because that is how we could excite some interest in this topic. Okay. So, there are lots of interesting possibilities to look into in the design of DRAM cache. Okay. I have stopped here. I have a few more slides which talk about our work in DRAM cache, but in the interest of time I will stop here. But you could talk to me offline about what is the kind of things that we are doing, how it kind of impacts in other architectures which have integrated CPU, GPU and things like that. So, there are lots of interesting issues and challenges that one could talk about, right. So, I'll leave here.